Hydraulics is the science relating to the behaviour of liquids under various conditions. In aircraft, the hydraulic system provides a means of operating large and remote components that it would not be possible to operate satisfactorily by other means. Hydraulic systems provide the power for the operation of components such as landing gear, flaps, flight controls, wheel brakes, and other systems that require high power, accurate control and rapid response rates. In this series of lessons, we will begin by looking at hydraulic theory, including the physical laws that apply to hydraulic systems. We will discuss the properties required of hydraulic fluids. We will look at the components that make up a basic hydraulic system, and we will see how this system can be improved by adding further components. We will examine the controls and indicating systems required to allow the flight crew to operate and monitor the system, and we will examine the components required for ground servicing purposes. Finally, we will look at a typical hydraulic system as fitted to a modern airliner. Bertholle Pascal was a 16th century French mathematician, physicist and religious philosopher. He discovered that if a force is applied to a liquid in a confined space, then the resulting pressure will be felt equally at all points. This fact is therefore known as Pascal's law, and is the principle upon which all hydraulic systems operate. However, before we get involved in Pascal's law, we first need to review some of the units and formulae used to measure pressure, area, force and work. The force acting on a liquid is the total load available and can be measured in newtons, pounds or kilograms. 1 kilogram equals 9.8 newtons or 2.2 pounds. Therefore 1 pound equals 4.45 newtons. Area can be measured in square inches or square metres. There are 1,550 square inches in a square metre. Pressure is force per unit area. It can be measured in pounds per square inch or newtons per square metre. In the example, we have an area 2 metres by 2 metres, 4 square metres. If we apply a force of 16 newtons to this area, then the force felt on each square metre will be 4 newtons. Thus the pressure is 4 newtons per square metre. In theoretical mathematics, the normal units of pressure are newtons per square metre. These units are often referred to as pascals. 1 newton per square metre equals 1 pascal. However, most aircraft gauges are calibrated in pounds per square inch, or psi. It is probably worth noting that a pressure of 1 newton per square metre is very small. It is equivalent to 0.000145 pounds per square inch. So the more commonly used metric units are kilopascals or megapascals, abbreviated to kPa or MPa. Another unit of pressure in use is the bar. You will have used this for altimeter settings. Standard pressure is 1013.2 millibars, or 1.0132 bars. 1 bar is equivalent to 100,000 pascals. So in some areas of the world, the barometric pressure is given in hectopascals, 1 millibar being equivalent to 100 pascals, or 1 hectopascal. The work done by a machine can be measured by multiplying the force applied by the distance moved. It is measured in joules, where 1 joule is equal to a force of 1 newton being moved through 1 metre. Work done is a form of energy, so we need to bear in mind that energy, and therefore work, can be neither created nor destroyed. Let us now go back to Pascal's law. Pascal stated that if a force is applied to a liquid in a confined space, then the resulting pressure will be felt equally at all points. If in the diagram the force applied is 10 newtons, and the area of the piston is 0.5 square meters, then the pressure will be 10 divided by 0.5, which equals 20 newtons per square meter, or of course 20 pascals. That pressure will be the same in all areas of the liquid. If we now increase the force to 20 newtons, what will the pressure be? Press continue to see the answer. The answer is 40 newtons per square meter, or 40 pascals. If we go back to our original example, but this time increase the area of the piston to 1 square meter, keeping the force applied at 10 newtons, using the formula pressure equals force divided by area, then the pressure will be 10 divided by 1, or 10 pascals. We can see from these examples that the pressure varies in direct proportion to the force applied on the piston, but in inverse proportion to the piston area. A simple hydraulic system, such as that shown, consists of two different sized cylinders connected by a pipe. According to Pascal's law, pressure exerted on the smaller piston is transmitted through the fluid to act on the internal surface of the larger piston. Pressure is a property of the system, not the pistons, and is therefore experienced equally by each piston. Because each piston has a different surface area, the force exerted by each piston will be different, even though the pressure is the same. Although in our example the pistons are close together, this does not need to be the case. The interconnecting pipe can be as long as required, and ignoring friction, it will have no effect on the system. It was this principle that was understood by Joseph Bramah when he patented the Bramah press in 1795. He observed two facts about his press. Firstly, the smaller the area under load, then for a given force, the greater will be the pressure generated. And secondly, the larger the area under pressure, the greater will be the load available. In our example, piston A has an area of 0.002 square meters, and we are applying a force of 1000 newtons to it. We know that pressure equals force divided by area, so this will produce a pressure of 1000 divided by 0.002, which equals 500,000 pascals, or 500 kilopascals. According to Pascal, this pressure will be felt throughout the whole system. Piston B has an area of 0.004 square meters. It will therefore be able to support a force of 500,000 multiplied by 0.004, which is 2000 newtons. If we now move piston A down 0.6 meters, then the work done, force multiplied by distance, will be 1000 multiplied by 0.6, which is 600 joules. Ignoring any losses due to friction, the same amount of work must be done on piston B, so it must move up 600 divided by 2000, which is 0.3 meters. We can see from this that for a given system pressure, the force produced will be directly proportional to the piston area, and the distance moved by the piston will be inversely proportional to the piston area. Now try this example for yourself. What will be the force available on piston B? The correct answer is 12,000 newtons. If you answered it correctly, then continue. If not, you may wish to review the lesson so far before carrying on. The Brahma press is a passive hydraulic system. A force is only applied to a piston, piston A in our example, when it is desired to move a load, piston B. Pressure is only generated when it is required. Although this is a very simple system, it can be extremely powerful. In 1846, Robert Stephenson used a single hydraulic press to hoist gigantic 1,144-ton tubes into place for his Britannia Bridge across the Menai Straits, between the island of Anglesey and the mainland of Wales. A smaller example can be found in many light aircraft braking systems. Here, piston A in the press is replaced by the master cylinder, the force being produced by the pilot's foot on the pedal. Piston B is now the slave cylinder. You will notice that we have added a fluid reservoir. This is there purely to keep the system topped up in case of minor leaks. For more complicated aircraft systems, a pump is required to deliver a flow of liquid into the system. It is worth noting that a pump in itself does not supply pressure. If it is pumping through an open-ended tube, then the fluid will have no pressure. In order for pressure to build, the flow has to be restricted. In aircraft hydraulic systems, this restriction is provided by movable pistons, which travel backwards and forwards in cylinders, known as hydraulic jacks or actuators. The power required for operating different services varies according to their size and loading. This can be catered for by using actuators with pistons of different areas for different work as required by the load, whilst keeping the pump output pressure constant. For instance, main undercarriage up jacks will need pistons with a very large surface area, whilst individual spoiler panels will have relatively small pistons. This is the end of the lesson. You should now be familiar with the units of measurement used in hydraulic systems. You should understand Pascal's law and have a complete understanding of the Brahma press, particularly the relationships between force, distance, and area.